Okay, so in reviewing the preliminary practice quiz, I see that people may want some pointers. Looks like a lot of people are hovering around 50%. So I want to give you some pointers, things to look out for. I'm not going to work out the answers in detail. I think at the graduate level, you should be able to work out details yourself. But if you have issues and problems, please make an appointment. I'd be happy to talk with you. All right, so this was the first question. And when you want to simplify things algebraically, you want to look for patterns. A very important pattern is right here, the difference of squares. You should be looking out for this. This appears much more than you may think. Okay, so the difference of squares gives you x minus y. And since the whole thing is to the x power, x minus y to the x, x plus y to the x. Okay. And look at these x's, that's quite important. You can get the x's here. There's an x there and an x there. There's an x here and an x there. All right, and you have the same factors up top. So you need to be able to cancel those. That is elementary algebra exponent rules. So I will not go over that any further. The answer is some fraction to the yth power. Now you can't simplify all the way down. Your answer still has x and y in it. But there's some fraction to the yth power is your final answer. Okay, second one. By the way, in the actual test, I do put the problems in the test and not have to take them from the book. So that should make things a little bit less stressful. This one was actually quite difficult if you didn't take the hint. It seems that people had trouble understanding what the hint meant. So I don't see anybody actually took the hint. It says take reciprocals and break the fractions apart. Then add together the equations. Take reciprocals and break the fractions apart. What does that mean? Take reciprocals. Reciprocal means 1 over. If I take reciprocal of this here, I have the x plus y over x. xy equals 1. Now the other terms are going to be similar. Then it says break the fractions apart. Look at what you can do here. It's going to be x over xy plus y over xy. And that's equal to 1. Okay. So now the x's cancel, so I get 1 over y and 1 over x is equal to 1. So you can see here, if you do this with all of the variables, you're really dealing with reciprocals of the variables. So one way to deal with this problem would simply be let y prime be 1 over y, x prime equals 1 over x, z prime equals 1 over z. You make those substitutions, then these equations really become quite simple. Right? So you can do that technique. You do this change of variable. You make that change in your 3 equations, you'll get 3 linear equations and 3 unknowns. And that gives 3 equations, 3 unknowns. Okay, all right. Okay, next one here. Here we have a conjugate on the top, 3 plus 8i conjugate, divided by 7 plus 6i. That gives me 3 minus 8i divided by 7 plus 6i. Now the way you get rid of complex numbers in the denominator is multiply by the complex conjugate. Okay, again, this is difference of squares, so that's going to be 7 minus 6i or 7 minus 6i, right? You can multiply and divide by the same thing. There's a 7 down there. And you should be able to do that. What you have on the bottom is difference of squares. Pay attention, there's no square root on the bottom. You have to work this out, and you'll get a real number on the bottom, and then you get a complex number using Floy on the top. You'll get a number of the form a plus bi. Your final answer should have the form a plus bi. And you should be able to find a and b in this case. Okay, the next problem is a polar problem. The problem specified that you should find this using polar arithmetic. Now, when dealing with polar complex numbers, you really should visualize, okay, and plot it. So let's see where these numbers are. They're very important to be able to visualize in mathematics. Einstein said, imagination is more important than knowledge. If you can imagine and visualize, you can go a long way towards solving these problems. Let's look at this numerator. 2 plus square root of 2 plus 2 plus square root of 2 to I. These are both positive, so it's in the first quadrant. In fact, they're equal, so it's out here on the 45-degree line somewhere. What is 45 degrees? Pi over 4. Right. This is 2 square roots of 2. This is 2 square roots of 2. Pythagorean theorem gives that this is 4. We can work it out. All right. How about on the bottom? Square root of 3 over 4 plus I over 4. Which is bigger? Square root of 3 over 4 is bigger. It's somewhere here. I'm not sure exactly where. Let me put it in a different place. But it's somewhere here. Square root of 3 over 4 and I over 4. So if I have square root of 3 over 4 plus I over 4, now this should look somewhat familiar because that's 1/2 of square root of 3 over 2 plus I over 2. And this here is the cosine and sine of 60 degrees or pi over 6. This is 1/2 times cis pi over 6. Right? And this one here is going to be 4 cis pi over 4. So what you have here is 4 cis pi over 4 over 1/2 cis pi over 6. All right, and you have your rules for dividing polar numbers. So remember, you divide the moduluses, and when you divide two complex numbers, you're going to subtract the angles. When you multiply two cis's, you add the angles. Cis pi over 4 times cis pi over 6 would be cis pi over 4 plus pi over 6. Cis pi over 4 divided by cis pi over 6 is the same as cis of pi over 4 minus pi over 6. Okay, so that's how it works. Kind of like exponential functions. Okay, now what about this next one? Again, visualization is the key. Let's visualize this complex number. Both parts are negative, so it's in the third quadrant. Both parts are equal, so this 45-degree line. This is pi plus pi over 4. So in fact, that's pi plus pi over 4. That angle is 5 pi over 4. Okay. What's the radius? Well, this is square root of 2. This is square root of 2. So in fact, this is going to be 2 right there. Work it out with the Pythagorean theorem. So what you have here is 2 cis pi over 4, cis pi over 4 to the 12th. All right? And then remember your de Moivre's theorem. Okay, and also you can reduce by 2 pi, right? If I do take this cis pi over 5 pi over 4 to the 12th power, that's going to be cis of 12 times 5 pi over 4, which is actually cis of 15 pi. Remember, you can reduce that down. You want your cis to be between 0 and pi. So final answer should have cis theta, where theta is between 0 and pi and 2 pi. You can always reduce it down. And in fact, in this case, the answer is, you don't even write it as a cis. In this case, you can write the answer as a number. It's a well-known number when you reduce this down and find out. Think about what 15 pi, what cis of 15 pi is. All right, so that's that one. Okay, next one is talking about UPC numbers. UPC numbers are a set of 12 digits that satisfy this modular equation. This one says, using this valid number, show that this number is not valid. This is a transposition, exchanges the 0 and the 3. All right. So we know that the top number is a valid number. So we have, if we want to write that down, the top number being a valid number would be, it's going to be 3 times d1. d1 is 0, d2 is 5, and so on. So we have 3 times 0 plus 1 times 5, ... Now let's see, this is going out to, this is a d2, d3, d4, d5, d6, d7. d7 is 3. And see, the odd ones are multiplied by 3. So this would be 3 times 3, that's d7. and d8 is 0. And then we have plus 1 times 0, plus dot, dot, dot. Now we know this is valid, so this is congruent to 0 mod 10. Okay? All right, now, what's the difference between this code and this code? Well, in this code, what we did was he added a 3 to d6. Well, here I said this is going to be the one before here's 1 times 0. Let me make that a little bit neater so you can see what's going on. So this is going to be plus 1 times 0 plus this, and this is d6. Okay, so since this is valid, we know this is true. I rewrote this a little bit more neatly so you can see. Remember, the sixth digit is 0 and the 7th digit is 3. That's going to be important in a moment. Now we want to check out this one here. This one is similar. I can write this one out. We're going to have digits here. The first one digit is going to be 3 times d1. So this is the second UPC code. This UPC code is 3 times d1 plus dot, dot, dot. Now here what's happened? The 0 has become a 3. So this becomes 1 times 3. And this becomes 3 times 0. And this is 1 times 0 plus. Now I don't know what this is congruent to. Let me just say it's congruent to A mod 10. Okay? Now suppose I can subtract these two. I can subtract these two. Suppose I do subtract these two. I can do arithmetic in mod 10 just like I do in any other case. If I subtract these two, this one becomes a minus 3, and this becomes a plus 0. All these others are the same, so these are all zeros. Okay, so that's equivalent to A mod 10. Okay, so that means that this second expression, the second UPC expression, is equivalent to minus 3 mod 10, right? Okay, well, minus 3, or it's also equivalent to 7 because you can add any multiple of 10 to make it work out. Okay, so it's not equivalent to 10, so it's not valid. Okay, well, you can think that way. Remember, you can do algebra with modular equations just the same way you do with regular equations. You can add them, you can multiply them, you can subtract them. You have to have that kind of facility. All right, well, this next problem illustrates a very important principle and one that's quite general when dealing with modular arithmetic. So you should always reduce your numbers before working with them. So always reduce your numbers. When working in mod n. Okay? All right, so 523. Since I'm working in mod 5, I can reduce 523 mod 5. What is 523 mod 5? Well, when you divide by 5, actually, if you can divide this by 10 because 10 is divisible by 5, you can see that if this is going to be divisible by 5 with the remainder 3. So this is just 3. Okay. Let's do another one. Suppose we have this one. Mod 4, 5, 6, 8, 5. Suppose I divide this by 5. Where 4, 5, 6, 0 is divisible by 5. So this has the same mod 5 as 8, but certainly 8 mod 5 is 3. So I also have 3. Okay? So I can replace this with 3. I can replace this with 3. In fact, I can replace this also with 3. I can replace this with 3. I can replace this with 0. And then I do the arithmetic. All right? So that saves a lot of work. Very important principle. Very important when you're dealing with modular arithmetic. And it's also useful in other problems in this practice exam as well. Okay, next one here, we have this modular equation here. 50m minus 17n equals 12. So if you apply the Euclidean algorithm, if you remember how that goes, we start off with these two factors and we write 20 and divide by 17, and it has remainder 3. So I get 3 equals 20 minus 17. All right. Now you could continue to reduce here. But this gives, for instance, the way I wrote this was 3 is equal to 1 minus 1, if you write this in vector notation. Now you could continue to work this down, which is possible, but actually in this case, we can do a shortcut. Notice that what you have here is you have 3 is equal to 20 times 1 plus 17 times minus 1. All right, now what do I want? I want 12. Multiply both sides by 4. 4 is equal to this. Okay, so I have 12 is equal to 20 times minus 4. Plus, 20 times 4, sorry, not minus 4. 20 times 4 plus 17 times minus 4. I'm writing a slash through my 7s just to make it clear. All right, so I now have a particular solution. Okay, and then if you want to find the general solution, you write this way: 12 equals 20 times n plus 17 times m. You subtract here, you get 0 equals 20 times 4 minus n, and then plus 17 times minus 4 minus m. Okay, and then you can bring the, I'll bring the 17 to the other side. I could bring the 20 to the other side, but I'll bring the 17 to the other side. 17 times 4 plus m equals 20 times 4 minus m. Okay, so for instance, this side is divisible by 17. The other side must be divisible by 17, so you can write 17 equals 4 minus n times, 17 k equals 4 minus n. And then you solve for k, solve for n, and then solve for m. Okay, so that's the procedure there. Follow that step-by-step procedure. I know that might be unfamiliar to some people, but it is important to be able to solve step-by-step procedures in algebra. Okay, next one here, also a modular equation. I'm going to emphasize again the importance of reducing your numbers as much as possible before you work algebra equations. So reduce your numbers. So what do I mean by that? Well, let me first simplify this. I'll bring the 60 to the other side. So that gives me 423x is equal to 720 minus 60 is going to be 660. And this is mod 101. Now 423 is equivalent to what? Well, 404 is divisible by 101. So that's equivalent to 404, and then, so that's equal to 404 plus how much? It's going to be 19. I think that's right. Yeah, because that's going to be 14, 19, so that's equivalent to 19. Mod 101. Okay, so you can replace 423 with 19. And what about 660? 660 is going to be 606 plus 54, right? So that's equivalent to 54, mod 101. Okay, all right, so to solve this equation, what you want is 19x is equivalent to 54 mod 101. Now you can do this a bunch of ways. One way to do it is you can go 19x is equal to 54, and it works out better if you say minus 101. I can say y, I suppose. And that gives you 19x plus 101 y equals 54. And this is just a Diophantine equation. Another way, which people do, is take this equation here. So an alternative is divide this by 19. You get x is equal to 54 over 19 minus 101 y over 19. And actually, I can rewrite this by taking the, I'm not writing as a mixed fraction. That first is 2 plus 6/19. And I can divide this out by 19. I'm not sure how many times 19 goes into this. I think it goes in 5 times. And then I think it's going to be plus 6y over 19. Something like that. Then you have to find y that makes this a whole number. Okay, we have 6 plus 6y over 19. I need to find a y that makes that a whole number. In other words, I need to find a y such that 6 plus 6y is divisible by 19. Once you've done that, then you have an expression for x. So 2 ways to do this problem, either Diophantine or to do it using this other method. If you want examples of this second method here, you can see example 536 and 537. If you want some examples to see how that's done. Okay, next one here, find the multiplicative inverse of 22 in Z51. What is the multiplicative inverse of 22? The multiplicative inverse is the integer in Z51 that satisfies 22n is equal to 1 mod 51. Okay, that's the same thing as saying that 22n is equal to 1 minus 51m, right? So then we have again a modular equation, 22n plus 51m is equal to 1. So I can solve this using the Euclidean algorithm or using that other method that I showed before. So I recommend you practice Euclidean algorithm because if you do Euclidean algorithm 1, if you can do Euclidean algorithm well, you can do all of these problems and don't have to think about it much. The other method often works, but sometimes when you have large numbers, it's somewhat difficult. All right, so that's how you do number 10. Okay, let's look at the next one, 733e. That brings us to here. So that's this one here, 733e. We're given a set A, and we'll let G be the set of all subsets of A. So again, let's try to diagram what's going on. We have A, which is some big set. And then all the subsets in A, we can draw lots of different subsets. All the subsets in A are the elements of G. Okay? So does each element of G have a unique inverse under the operation intersection? Okay. So first of all, we need to find the identity. The identity under intersection. So the identity under intersection would be, let's call that, I'll call that I. Okay. I must satisfy I intersect, now I can take any subset here, which I could say B. I intersect B must be equal to B for any set B, which is contained in A. All right, so that must be true for any old set. So a little thought should convince you that I must be equal to A. Because if I don't include all of A, then I could take the complement of whatever set I take, and that would have no intersection. So it would not be equal to the set itself. But certainly if I take the entire set and intersect it with any set, that will give me the same set back again. But again, if I don't include the whole set, I can certainly find a set that does not intersect with I, and that will cause me a problem. So what I want, so how about inverse? Inverse means if I have a set B, the inverse of B is a set, and let me just call it, I'll just call it B prime, just such that, actually B prime is not so good because that's what we use for complement. So let's just call it C, such that B intersect C is equal to the identity. Right? Now, in this case, the identity is equal to the entire set A. All right. So can I always find, for any set B, can I always find another set C whose intersection with B gives me the whole set? Sorry, the inverse of B satisfies, the inverse of B satisfies B intersects C is equal to A. All right, now what do we have here? We have A, which is this big set here. We have B, which is inside. We have C, which is inside. How can I get the intersection of two sets inside of A to be all of A? It's not possible. For instance, if I take B is equal to the empty set, has no inverse. Because it's not possible to find C contained in A such that C intersect the empty set is equal to A. In fact, any set intercept the empty set is going to be the empty set. So it's not true. So intersection doesn't have unique inverses. In fact, the only set that has an inverse is A itself. No other set has an inverse. Right? So that's that one. Okay, next one was list all one-to-one functions from the set A1, 2, 3 and B minus 1, 0, 1. Okay, so if we draw the picture, we have our two bubbles. We have the A bubble and the B bubble. We have the domain and the codomain. So my domain would be A right here. Here's my set A, and it has the points 1, 2, 3. I have my set B, which has the points minus 1, 0, 1. Now, if the function is one-to-one, that means there's at most one arrow into each element of the codomain. All right. So if I'm going to just diagram that schematically, there's at most one arrow into each element of the codomain. Now, there could be less than one arrow, but I also know that there have to be 3 arrows going out. All right. If there are 3 arrows going out, there must be 3 arrows going in. And in fact, any one-to-one function must also be onto. So the question is, how many ways can I connect up these arrows? These have to connect up to here. Now, actually, so I need to connect the arrows out with the arrows in. And as someone pointed out, very good observation, there's actually 3 factorial, because I'm basically choosing the different ways to assign minus 1, 0, and 1 to these 3 numbers. So there's actually 3 factorial different one-to-one functions. And you should be able to list them. One way to list them is by this 2-column. So this would be, I can call this x, and then I can call this f of x. All right, so this is going to be 1, 2, 3. Right? And f of x here, I could do minus 1, 0, 1. Okay. Now, let's see, how many ways could I do this so that 1 goes to minus 1? All right. Now, if 1 goes to minus 1, if I set 2 to 0 again, then 3 would have to go to 1, so I can switch these 2. Now, on the other hand, I could have 1 go to 1, in which case 2 could go to minus 1 and 3 go to 0. I could also have 1 go to 1, and 2 go to 0, and 3 go to minus 1, okay? And then you can find 2 more. Okay, so you want to find a systematic way of listing functions. Right. So you might, for exercise, you might think about how you would think about this in finding onto functions. In fact, the answer is the same because, as we've seen in this case, in this particular case, a function is onto if and only if it's one-to-one. But that's only in this particular case when the number of elements of the domain is equal to the number of elements in the codomain. My next one was to prove that this function, to decide whether or not this function is one-to-one. Again, the power of visualization. These are the natural numbers. Natural numbers begin with 1, 2, 3, etc. Okay? According to the book, that's how natural numbers are defined. Okay, so let's take a look and see what f does. So if this is n and this is f of n. So let's see what the results are. If I put 1 in here, this gives me 0, so this gives me 1. If I put 2 in here, I'm going to get 1 times 2 times 3. Here I'm going to get 2 times 3 times 4, etc. Okay. Now, one thing to notice is that f is strictly increasing. So that means that if I have two numbers, so if I have, say, n and m, if n is greater than m, that means f of n is greater than f of m. Okay. On the other hand, if m is greater than n, then f of m is greater than f of n, right? So if I put these two together, that means that if if n is unequal to m, that means that f of n, put this place, that means that f of n is unequal to f of n. Okay, on the other hand, if f of n is equal to f of m, then it's not possible for n to be equal to m, okay? Because m is not greater than n and m is not less than n, okay? Okay, m is not greater than n and m is not less than n, okay? So that means that m equals n. Okay? This statement is actually the contrapositive of this one. Okay? So therefore, that means that f is one-to-one. Actually, this is the other way of showing that function is one-to-one. We have done before, f of n equals f of m implies m equals n. Another way of saying that is n is unequal to m, that means f of n is unequal to f of m. Those two statements are contrapositives of each other, all right? So this statement here and this statement here are called contrapositives. Now I can refer these two definitions to you in the book. Definition 836 says f is one-to-one if for all a1 and a2 in A such that f of a1 equals f of a2, we have a1 equals a2. That's this way here. If f of n equals f of m, that implies m equals n. So that's what it's saying here. On the other hand, if we look for the word contrapositive, so we have definition 8315. F is one-to-one if for all a1 and a2 such that a1 is unequal to a2, we have f of a1 is unequal to f of a2. That's the statement here. And unequal to m implies f of n unequal to f of m. So these are both equivalent ways of showing that f is one-to-one. Okay, so just to make that clear, f is one-to-one if either of these statements hold. Okay, and they can say, as I said, they're contrapositives of each other. All right? All right, next problem was to show that this is onto or not onto. Determine whether or not P is onto. So that's the next problem here. to determine whether or not P is onto. So that means that I want to say, given Y in the codomain, in this case, the codomain is R, I need to find an X such that P of X is equal to Y. Okay, so I should say, can I find an X such that P of X is equal to Y? Well, let me go ahead and set it true, set it equal. And where's my mouse? We'll get there. Okay, here we go. Okay, so we can set, so this means 3x plus 2 is equal to y. And that means I can certainly solve for x, that x is equal to y minus 2 over 3. Now, y minus 2 over 3 is in the domain. Is in R. And if you can verify that P of y minus 2 over 3 is going to be equal to 3 times y minus 2 over 3 plus 2, okay? And that's equal to 1, okay? All right, so that means that for any y in the codomain, I can find an x such that P of x equal to y, okay? So P is onto. Okay. Now notice that if I had changed the domain in this case, I might not have an onto function. So you can think of what kind of examples that might be. For instance, if I have a domain which is an interval, you may not have a onto function. Okay, next question was this one. The question was to determine whether or not G is onto. So in other words, given any z, any complex number z in the codomain, which is all complex numbers, is it possible? Let me say complex number W. We can say that like that because we are already using a z. Is it possible you find a complex number, a non-zero complex number, z such that z inverse is equal to W? Is that true? Is it possible to find for any complex number? Is it possible to find a number whose inverse is that number? Now, in many cases, it is. For instance, if I take complex number I, the inverse of I is minus I. The inverse of 1 is 1. Inverse of minus 1 is minus 1. So many complex numbers do have an inverse. So note that 0, however, does not have an inverse. So there is no, and there is no number, there is no complex number, whoops, what's going on here? There's no complex number. Let me go back here. Whose inverse okay? So that means that 0 is not in the range of G. So G is not 1-to-1. So G is not onto. Okay? Because there's no way to find a G of Z such that G of Z equals to 0. Okay? All right, we're almost there. Okay, last question was, is G a bijection? Where G is a function given this way, from integers mod 9 to integers mod 9, G of Z equals x modular multiply 3 plus 3. All right, so let's see. So if it's a bijection, that means that it's both one-to-one and onto. Okay. Now, one way to do this is simply list g of x for all values of x, because Z9 only has 9 elements, so that should be easy enough to do. Another way is simply to notice that if I put 3 in here, I get 3 circle dot 3, which is equal to 0 mod 9, and I get plus 3. So notice that g of 3 is equal to 3. On the other hand, if I put x equals 0, I also get 3. All right? That's enough to show that the function is not one-to-one. So g is not a bijection. Another way to notice is that g of x is always going to be divisible by 3. You can think about why that is. Right? So as I said, a lot of people are running about 50%. That's fine. This is if you did better than 50%, you should be proud of yourself. The takeaways I want you to take away from this presentation: visualize, make sure you have, you need to have basic algebra competency, which comes into a lot of these questions. There's more than one way to do a problem. Don't waste a lot of time on a single problem. I think maybe people might have wasted too much time on the second problem, which, as I said, was quite difficult unless you found the right way to do it. So if you find yourself getting stuck, spending more than a page on a problem, better go on to the next one. All right. Okay, hope that's helpful. And feel free to ask me any questions.